to give us his presentation. Welcome, Albert.
Albert, thank you.
Okay, please go ahead.
Okay. All right. I thank you all for the opportunity, and once again, you are all welcome here. And this topic is going to be, as much as I can, to be in a very normal, basic level for everyone to be able to understand basic things that happen around engineering in radio telescope. So today's topic is choosing how a radio telescope is designed and developed. And we see MSA, which stands for, we take the case study of Mauritius Small Array. Okay, so let's dive into it. First of all, I'm a PhD student at the University of Mauritius, and my appreciation acknowledge goes to my supervisors right here, and also to DARA, that is Development in Africa with Radio Astronomy, who founded this particular research. Okay. Minimize, okay. Okay, so first of all, I'm trying to minimize this from there. Can you try from how to minimize this? The panel, okay. I think this is better, okay. Okay, so when we say what is telescope, so in a basic understanding of where you say telescope is an instrument that makes distant objects. So anything that is very far away from us, telescope makes it closer, or make it appear closer, or more detail about, so all is about collecting light and magnifying that light for our view. So if anything that is about kilometers that your eye cannot see, this is a work that telescope does, is able to bring this thing very close to you or closer. So sometimes if you have these spectacles that maybe your vision is a bit low, and you happen to maybe go to the hospital and see the expert, what they do is to probably give you a magnifying glass or spectacle that you'll be able to read or bring this vision closer. So before that, okay. Let's see. So we have types of telescopes in our domain. So from here, we have an optical telescope. That is what we have here. This is mostly what we know about, or we are very familiar with. We have a radio telescope. There is also this one that is you see in this picture. We have infrared telescope, we have X-ray, and we have gamma ray. So some of these are telescopes that probably are not built on ground, and some of them are in space, especially the X-ray and the gamma ray. But this very infrared one is built on ground. And from there, we zoom into radio telescope. So that is what our focus today is going to be on, radio telescopes. So a radio telescope is a special kind of a telescope that listens to radio waves from space instead of looking at light. So what we are talking about here is the types of telescopes that I've mentioned earlier on. In that, we call something magnetic spectrum. In that spectrum, where we have different lights, spectrum from different lights, we have the visible one. That is what our eyes can see. That is why when we look up into the sky and we use that optical telescope, it's called optical telescope, we'll be able to see some of the objects or astronomical objects with our naked eye. But beyond that, some of these astronomical objects emit in different wavelengths. This or wavelength or spectrum, some are radio And I mentioned about infrared, I mentioned about X-ray, and I mentioned about gamma ray, which I show you they are telescope earlier on. But within this one, some emit radio. So the electromagnetic, or let me call it the lights that are coming from this astronomical objects or celestial objects, they are radio, in radio form. But our eyes are not designed to be able to see these radio waves. Therefore, a special kind of instrument or telescope is designed to be able to see this radio or collect this light in radio form and be able to transform them or do where the engineering or other scientific works are being done on it until we see what is happening in that spectrum. So this is what happened. That is probably basic understanding or basic explanation I can give in this context. So what did they do? We look at these radio waves, of which we use maybe dishes or satellite dish to collect these waves, to look at the stars, the galaxies, other objects, the planet, and study more about them. So that is that. So some examples of radio telescope. For example, this is a radio telescope on its own. Basically, what we call it helic antenna. So this is probably located in at the Mauritius radio telescope. This helic antenna is a radio telescope on its own. When you look here, we have about 2,000 of these species formed in a T shape. That is one. This is another radio telescope, and the same as this one. This is the collecting surface, and this is a full view of it. We are very familiar with this one. This is what we have. This is our own right in Ghana. That is. Then we move on to the key factors for designing radio telescope. Naomi, can you please keep admitting those who are behind? Either Naomi or Stephen. Okay, let's move on. So the key factors.
Okay, I will.
When we are to design a radio telescope or we are to build a radio telescope, these factors, measured, we call them the research objectives. Before you build a telescope, you must look at your research objectives. What do you want to do? What are they? What do you want to research on before? That is the first question and a major question you have to look at before a telescope is being developed, or it is even dream about before you dream of any telescope. So if you see all the telescopes that have been launched, or maybe space rockets that have been launched, satellites that have been launched, or whatever, the research objectives comes first before we begin to think about them. So let's look at them one by one. So these research objectives, first of all, must define the primary, the primary scientific goals. They might define your primary scientific goals. Number two, such as studying the pulses. So if it's a pulses that you want to study, it must form part of that. Whether you want to map the distribution of hydrogen line in the galaxy, that is one of them. Whether you want to detecting the cosmic microwave background radiation or search for extraterrestrial intelligence, all forms about that. So from that goal or the research objectives, we then move to the engineering factors. So after we have our research objectives, that either want to study the distribution of hydrogen line, where we know the formation of stars and the planets are being formed, or you want to study about the process or methanol measures, and some of, if you want to do astrochemistry and other stuff, that's maybe Dr. Naomi and co study about. From there, the scientists will now move to the engineers that this is what we want to research on. Then the engineers will begin to look at that. Then they will look at these factors, the antenna design. Sorry. Number two, they'll look at the location. So if we are studying, so for example, some of these telescopes, you see some of them needed to be in a desert or have to be some thousands of kilometers above sea level, where there is no moisture. So these are some of the factors. So we talk about some of these things. So location is one of the crucial areas. For example, if we see where Ghana Radio Astronomy Observatory is situated today, then it was very far away from settlement. And as we speak now, that the settlement has come to meet the observatory, it is probably going to affect its operations. So they might have to look for a place far away from settlement in isolated. So if you have been to any of these observatories before in the world, most of them, about 90% of them, are in isolation. They are far away from settlement. Some you have to take maybe helicopters and other things too. So these are some of the factors that I have to go into consideration. So I am making or stressing on this location so that we that are here today will become agents of education or educate people who might be having the intention of going to build closer to the observatories that we have. Environmental factors, whether we are in the region where there's too much rain or we are in a place where it's closer to the sea, these are the factors that have to be taken into consideration. And number four, the receiver system that have to be designed, because each science that you have to do have to come with the receiver and the data processing design that they have to come with. And that follows you the mounting system and the tracking system. So what kind of telescope do you want to build? How do you want to track? Or how do you want the mounting to be? I know we have equatorial mount or alt azimuth. So these move as according to the movement of the Earth or the rotation of the Earth. So which one is suitably done? So these ones have to go into consideration. Then you have calibration and accuracy. So these are some of a bit more or less technical thing, but if you talk about calibration, you want to put it in some kind of standard. What are the standards that you'll be able to see that? So if you don't have that standardization, you will not be able to do the science that you want to do. So standardization and accuracy is also important. Another thing is budget and funding. That is the most important thing. And one of the most expensive instrument that is being built, or some of the most expensive instrument that is being built, is these radio telescopes and maybe rockets or space telescopes that will go and do some research that we don't know. They are very expensive. So there must be a budget, there must be funding. There must be funding. That is a key factor as well. Collaboration is also very important. This is not the all, but last but not the least, collaboration is a key factor over here, because you need to work with people from all aspects of expertise. Those with carpenters, masons, plumbers, welders, painters, those with cook, so many people have to work together to be able to achieve that goal. So these are the very key things that we have to look at. So we are now zooming into the MSE, as I explained earlier on, that is Mauritius Small Array. We are zooming our discussion down to this particular small design. So first of all, as I mentioned, so now we are now bringing all these objectives that I mentioned earlier on. What was our objectives when we were designing, or we talk of designing this small array? Number one, we want to study the galactic hydrogen emission. That was our scientific goal. This is the research that we wanted to do. So we have that. So we ask the question, before you study or do research on the hydrogen emission or galactic hydrogen emission, what instrument is required to do that before we move into that? So our objective number two, we want to build a prototype telescope array as a pathfinder for future SKE2 in Mauritius. So the SKE means the square kilometer array 2, phase 2. So as we speak now, there is a global project, which is a global square kilometer array that is supposed to have a telescope across the world, and more specifically in Africa. South Africa is currently hosting that project, and Australia in Africa, and Australia is also holding the other part of it. So 8 countries in Africa have been selected to have substations, meaning that a telescope will be built in each country and will connect them together and do one scientific research. The reason why we have to do this is that, one, we cannot build a telescope that is big as a square kilometer, the infrastructure, and it is not possible. So therefore, the scientists have come out with that particular idea that, okay, we need to build telescope in 8 partner countries to be able to achieve that goal. And Ghana happened to be one of them. Mauritius is one of them. Kenya, Botswana, Mozambique, Namibia, Madagascar. Yes, so these are the countries that are part of it, and South Africa is the headquarters. So Ghana have already had its share, and our 32-meter radio telescope is already in operation at Kutwese now. So when you see that, you know that we are part of that network of the square kilometer array. So that phase 2 that I talk about, Ghana happened to be part of it, and Ghana is the first among the 8 countries that built its or converted its old satellite dish into radio telescope. So our objective or aim was also to build a pathfinder in that country. Before Ghana built it or convert the telescope, scientists, engineers from Ghana Space Science Institute went to South Africa to build a miniature or prototype to see how it's going to work and how to learn about it. So it was one of the reasons why we are doing this. And also want to respond to the SKE2 technical engineering challenges, system verifications, because there might be challenges that will come, each country with its challenges and things. So these are some of the things that we wanted to address ahead of this particular global instrument. We want to provide astronomical experimental tools for risk.
Hello, Albert. I'm sure somebody has called him. Hello.
Please, am I on? Is my presentation on?
Yes, you are back online.
All right. Okay. Thank you. Can you remind me where I lost from? Is it
You
from
said
this slide?
Ghana is the first to convert our telescope.
Okay. Thank you. Yeah. So so basically I was on this point. So so Ghana was the first to convert its telescope and is part of that network. And here I was talking about we want to respond to the technical challenges and the system verification. So some of these systems may not be, or the countries may not be different, may not be same, and will be different and different challenges, technical challenges. So we need to address some of this. Again, we want to provide astronomical experimental tools for astronomy research in Africa. So some of us may not be privy to opportunities such as this instrument. If any student wanted to experiment on them, unless the data is deduced by someone already, then we will go and look at the data and just finish our research. No, we wanted to have such instrument where we can also go to it and start the study from the scratch. Again, we want to increase interest in astronomy or space science in Africa. So these are the basic or objectives that why we are building what we are doing. Now we are moving into the antenna design and the development. So the mechanical work involved, the civil work involved, electrical electronics, the RF, that is a radio frequency control monitoring system that involved in the building. First of all, I did mention about from the scientific research antenna design, we talk about the location. Well, so here the wind load analysis. Before we start, we've already known, or I know that in Mauritius, they are known for their cyclonic situation. So they are in a cyclone zone. And every year is something that they don't miss, just like us, where we also don't miss our rainy season or harmattan season. So cyclone appears almost between November, December, January, February, March, thereabout, to a extent where the entire country sometimes will be shut down. No activity, no commercial activity will happen. So if you design such an instrument or build such an instrument without taking into consideration of this weather or location, it's nothing, because the cyclone will come and just blow it off. So we start the analysis, and these are the summary of the analysis. We took into consideration a wind velocity of 300 kilometers per hour. 300 kilometers per hour, that's a wind speed. So in recent time, we haven't experienced up to 300 kilometers per hour. I think the highest we have attained is around 120 kilometers per hour. But in history, back in history, so we took into consideration a data of about 40 or 41 years ago, when such situation has been recorded, that they have experienced wind speed of 300 kilometers per hour. So we took our data, or I took this into consideration, and I start the analysis to be able to design the antenna. So meaning that this antenna has been designed so in such a way where the system will be designed that cyclone will reach above 300 kilometers per hour. That is where our antenna will begin to see any effect. But we have put some other mechanism in place. So I'll show you somewhere here. These are the column structures where we go through after getting this analysis, all these calculations, this comes with the mathematical calculations analysis. Then we move on to the software and do all the software or 3D modeling and do the testing. So we've also done a safety factor of 5.178, meaning that if 300 kilometers per hour is the highest, what we call a wind speed that can break this antenna, so you have to do that by 5, multiply this by 5. So you can just imagine. So the antenna column or structure is strong 5 times 300 kilometers per hour. So these are the engineering analysis that have to go into consideration. Again, once this tower design is complete, now another thing is that we come to the tower base plate and anchor, where we do the concrete work, the bolting, and all those things will go. Those places must also be strong enough, and this column must be able to fit into this well enough to be able to achieve the same purpose that we are trying to achieve. So these are just some numbers, the both sides, the length, the diameter, those things are more data. So here we come see the 3D drawings of the telescope, each part, and how we do the testing, how it will fit the brackets, and how the whole fitting will look like. When we were done with this drawing, we now test or do simulation, put all these values, these mathematical models, into this simulation and see. So you could see to which speed or which force that this antenna will have any internal vibration that will be able to affect some of this. And after the simulation analysis, we see that this will not be able to have any significant effect on this telescope. And once you are building a radio telescope, it must be steady as much as possible, so that when you are receiving or you are doing observation, you don't have this kind of distraction in your data. So we move from those design. Now we are done. We know that this is what we want to do, and we have all our models down or the print out. We just take it to the fabrication. So you can see here, we are doing the fabrication works. It started with the testing. So basically, when you see this picture here, those of you have been to the Ghana Radio Astronomy Observatory, this is just a typical dish. This is how it looks like. It's not a steerable one. When it's a steerable, not movable. But we are trying to convert this to become a trackable or moving dish. So we have to do a lot of mechanical work. So in astronomy, mechanical work is involved and that. After we're done, we are now look for design the control system, the motor, the drive system that will be able to fit on that. So we have to do some other analysis of prototyping, test them, and these are just the specification of this drive system as well. So we move to the concrete work, and you can see here, this is what we did, the concrete platform. We have to design all this according to the earlier drawings and simulation. Make sure that if we have put in the block, then the height, the kind of iron rods that have to go into, the bolt rods, the length, how deep they have to go into that concrete. And you see the fastening and make sure they all fit into the alignment that the column will be able to go on top. So you could see here, we are work and myself here, we are trying to get all those things. And you must make sure that exactly what you have designed or the plan you have on paper must meet that purpose. So, so after that column from previous, see, this is what we were able to put up together, and all our column fits together, and the dish conversion, the welding and other things bolting into the tower also fits accurately as how we wish or we want it. So after that, we noticed some, what do you call it? Some certain things did not really work well because how we wanted to rotate, and we have to bring it back and redo the alignment or rework on the same thing until we'll be able to meet this. So if you take a close look at the previous, you see, if you look at this and look at what we have here, you can see that there's a difference between the first one and the second one. So this is how engineering work. You go, you do the first thing, it doesn't work, come back to the drawing board to work on that. After that, the feed system. The feed, that is the first thing that receives the electromagnetic waves from the space and take it to your receiver system. So when it hits the surface of the electromagnetic waves, hit the surface of the big dish, reflect back to this feed. So again, after getting the design, we have to take it to the lab or the workshop and fabricate it, do some testing, and here we have it here working. So this is a testing and simulation. You cannot just do it and come and put it. You have to do simulation and see whether you are within that line. Then we have the receiver front end design. So these are the antennas. Supposedly we build 4 antennas similar, and they all look similar. And from the antenna, we have the other electronics travel from there to the lab where our receiver system is. So you have to put all this. So this is the block diagram of the receiver, and that is how it looks. So this is how the receiver looks like, and we call it a snapboard. It has its also meaning, and just leave it that way for now. Then we continue to the receiver parameters, because you need to check again whether the parameters that you have for your receiver and to be able to do the scientific work or research that you are looking for. Now, so in complete of that, putting all the system together, all that I talk about, a piece, all will join together and become one instrument. So this is the front end look of our rack system, our control system, our receiver system. We put everything throughout. This is the back of it. Look, a lot of cables, and you have to take critical look at it before put all this electrical and this electronics together, and each will be responding to each other one after the other. So that is what it all entails in designing the telescope or antenna. So after that, we wanted to again know that, okay, do I need to be going to the field each time if my antenna is working or if my antenna is not responding? How do I know? So basically, we have to also design the remote control or monitoring system. So you can just sit in your lab and monitor all of them through a camera. Just sit. It'll be somewhere here on your lab, on your laptop, wherever you are in the world, and monitor all this and control them as well. So this is how the entire setup look like. These are all the dishes, like from, if we are looking for, so this is in the west to east direction. So if you are in the western region or you are in the west direction and looking towards your east, this is how it look like. If you are in the south and looking towards the north, this is how they look like they are 4, but one is disappeared over here. Okay, sorry. Okay, so again, putting all the antennas together, you want to see how they are all responding to the signal. So these are the signal, and each of these coloring or spectrums also respond to each of the antennas. And this is how they respond, antenna calibrations, or can you see antenna 1, 2, 3. So we want to see, and you'll be able to do the calibrations and accuracy. As I mentioned earlier on, you see that, make sure that all these antennas are in line. And when they see one source or astronomical source, you will all be seeing it as one, not differently or different location. They all seeing one thing at a go. Very good. So after looking at the sun, we measure, we call something baseline visibility. So we have 4 antennas, and we want to measure between 32 meters. They are 32, 32, and up to 64. So in between, from here to here, this is a baseline. What do we see? How do we see the sky or see the sun? So these are the other things that I want to leave it low so that we don't get people confusing. So the same thing when we go to 64, what are we seeing? And yes, we can tell ourselves that we are seeing things equally, the meaning that our fringes or visibilities are all right. That is the same form of calibration and accuracy I talked about earlier on. And then we want to now measure or do part of the science that we are doing. We test our H1 measurement, which is our hydrogen emission that I mentioned, that is our key research we want to do. And we're able to detect this signal from within the galactic hydrogen. There's a H1 measurement. So yes, our antennas are working. And alongside, we also look at Sagittarius A, which is one of the galaxies up there, and we're able to see this plot. So these are the results, or these are the things that give us confirmations that yes, our system is responding accurately. So we put a publication on some of our results or the work that we've done. So if you're interested, probably you can search for these papers and read some further details about this design and its work. So yeah, so in summary, we said that as we develop the instrument, the Pathfinder for experimental astronomical tools for research across Africa, yes, we are towards that, or we almost achieved that goal. Develop skills towards the SKE2 technical engineering and systems verification challenges. Yes, we have achieved that goal. So these are the checkpoints when you do all these tests and do all your research, and be able to come back to be able to take all your objectives that you will be able to use. So teaching and learning tools for outreach. Yes, so we can use this and teach, and the center use for outreach. We have achieved that goal. So increase young African interest in STEM objects. Yes, so we can say that we have achieved that goal. Okay, so here I just want to show you some quick 2 minutes short video on how maybe basically we put some of this thing together. Somebody may be asking, how did you do this? So take a 2 minutes and let's look at it. Hope this is visible, right? These are the trend that we design. So we are trying to put the things and see some of the exercises that are possible. There is an absence of a typical train that lift this up and put it out. But then that is not established. line of one clip. That is all the see how that is so. Okay, so thank you so much, and your questions. Thank you.
Thank you so much, Albert, for taking us back to the basics. Thank you for your presentation. The floor is open now for any questions. We have 15 minutes. So if you have any questions, can you raise up your hand in the chats or using the raise hand icon, and then we can call you to ask your question. Okay, before anyone asks their question, I want to ask, were you there when we were installing the dishes, Albert?
Oh, you did not see me.
You were the one walking up and down in the blue shirt.
I was, yeah, I think it's the blue or ash or so, like some green. It was up there.
Oh, that's amazing. Okay.
Yeah.
Well done. I'm happy. I'm happy you were in there somewhere. Okay, I can see Sarah's hand. Sarah, you can unmute yourself.
Actually, this was our work, like two of us, myself and my colleague, all from Kenya. So from the scratch to the finish, this was our work. Yeah.
Oh, that's amazing. Okay, well done. Sarah, you can unmute yourself and ask a question.
Okay, thank you. It's more, well, a comment and then maybe just a small question at the end. So just to say thanks, Albert, for that. I think it's really interesting because, I mean, well, you know me and not maybe most other people here, maybe not everyone knows. I mean, I'm more on the astronomy education and outreach side. So we just think about, the telescope, getting the information and, the wonderful pictures and all that sort of thing. We don't really think about what goes into getting the telescope there in the first place and actually making it work. So it's actually really fascinating to see all the work that has to go on, if you like, behind the scenes first. I mean, even like I said, the digging the foundations and working out the stresses and all those things. I'm sure most of us don't really think about those things that have to be done first. So thank you for that really interesting background. And so my question was just, I mean, so right now, I mean, what's happening with that array now? I mean, who is using it and what kind of things is it used for?
Okay, so I must say the first part is complete, and we wanted to go or dive deeper into part of the research. So yes, we are still working on it. We are still using it, but up to a point where it will be now available for anyone who want to do any further science in that. So, but that is not open yet because we are still using it for further research.
Okay, thank you, sir, for your question.
Okay, thanks.
Say first, I can see your hands raised. You can unmute yourself and ask your question.
Okay, yeah. I joined very late because I was on the network.
Please, can you raise up your voice a little? We can't hear you well.
Yeah. Very late because I had a very bad network at my end. Yeah, my question is, I saw that where they saw the telescope is almost, the environment is full of trees. I don't know whether these trees will not obstruct any observation that they want to do. So I just want to find out whether it's possible that any observation that they want to do is placed within the environment where the installation is done.
Okay, thank you, Cephas. Albert, did you hear him? He said that would the trees obstruct the work you are doing because you can see a lot of trees around where you have installed the telescope.
Okay, so when you see maybe back some of the slides, you see that those trees were cleared. And one thing is where we're in the typical forest. And also one of the strong regulations over there is you cannot just stand up and cut trees. So we decided to finish building before we trim trees that are necessary. So the test, we point antennas towards some directions that require trees cutting before they were cut. So here, as you are seeing this photo, the trees at that time were building, but when we're done, those trees were cut. Let me see. Yeah, you could see here that some trees, the trees are no longer there, right? Yeah, you can see some trees are no longer there. Yeah, they were fell there with all of the trees after that. Yes, thank you.
Okay, thank you. I can see Biruk Abraham's hand up. You can unmute yourself and now.
Thank you very much.
Okay. Thank you, Albert. That's a great introduction for us. I think we've been talking about this one, and I want to ask you, like, what is the production cost that has been cost you to finish this project? Because I have been telling you to have this kind of project in our country too. So, yeah, that's it, Albert.
Yeah, hi, Biruk. Thank you for joining. Joining from Ethiopia. Yes, this question is not it's not a straight question. It's not a straight answer at all, because I did mention earlier on that location matters. It depends on where you are installing this. And here, a lot of things have gone in terms of funding. Money has gone into this, because constructing this concrete platform, advantage was that this was the old area and we have to build on this. And this area, the entire area is very rocky. And the kind of reinforcement that we put for this due to the cyclonic condition, the location and the weather. So it's my varied. But if you want me to give you ranges, between about 10,000. Oh, I want to, should be 10,000 to 30,000 euros or so, if I may not be mistaken, depending on where you are coming from or what your location. So it's not a straightforward answer, and a lot of visibility study have to be done before you come out with that fixed or accurate figure.
Okay, thank you.
Okay.
Any other question from the participants? Thank you, Biruk, for your question. Any other question?
Hello.
Is there one more hand up? I'm not seeing. Okay, Justice, please.
Yes, hello.
Yeah, hi,
Yes, we can
Justice.
hear you. Please speak.
Okay, thank you very much for this practical presentation. My question is, you talked about galactic hydrogen emission. My question is, the galactic, I really don't understand the galactic. We know of hydrogen emission, but why the galactic? And the second question is, you showed us electronic designs. I wanted to ask if those ones, they are done elsewhere, or you, the engineers, you built all those electronic gadgets before mounting them. And the third question is, how long does it take to construct a telescope of such nature, and what are some of the challenges? Do you get to a point whereby things are not going well, that you maybe financial or any other challenges, and where do you normally get your funds, and also the allocation? Maybe is it government property or private properties, and yeah, because of time, let me end my questions here. Thank you.
Okay, thank you. Dr. Ambi, would like to take the first one, and I can take the rest.
What's the first question? Sorry, the questions were low, so I'm now focused on the last one. The first question was about
the galactic hydrogen emission. What is why the galactic?
Because you know, the universe is made up of mostly gas and dust, and the gas that we are talking about, 90% of it is hydrogen. So if you want to know what's in the universe, you have to follow the hydrogen. And so if you want to study a galaxy, the molecule you want to study is hydrogen, because 90% of the galaxy is hydrogen. So that's why we study galactic hydrogen. And so for most of the objects in space, we look for the spins in hydrogen. That's the 21 centimeter hydrogen. Apart from that, if you want to know the molecules, the molecular weight of the object, then you look at the carbon monoxide or the carbon dioxide. And then you follow up with other analysis. But the premium or the primary molecule that we use to identify objects in space is hydrogen. And that's why we look at galactic hydrogen.
Thank you.
Okay.
Yeah, thank you. So the last one, talk about who owns that facility, whether it's government. And typically, I think it's owned by the university, because it was built at the university's facility. But the entire observatory, so both the university and the country, because the observatory is owned by the country and managed by the university. So once the university is the property of the state, so technically that. But because this project was funded by DARA, Development in Africa with Radio Astronomy, they have also full responsibility over it to give access to students or whoever wanted to research or use that facility. So that is that. Funding. So this project was funded by DARA, as I mentioned my first or second slide. I acknowledge DARA for sponsoring this particular project. Yes, it takes a lot to build radio telescope, and it is not easy for individual to build this. I did also mention about collaboration, and this where there was a collaboration between myself and my colleague Paul from Kenya. So whilst one was working from, let's say, from inside, one was working from outside. So when you look at all the outside structures and talk about all the physical structures, the disc conversion, the mechanical, those structures, all these were things that I built. We built all this. But in there are some components that we bought. We outsourced them on the shelf. We bought them and put them together. So by putting all this together, putting all the components, those electronic stuff together were things. And when you look at this receiver, this is a receiver. It's a very, very small, a very something tiny. So the receiver just came in this circuit board. So after it has arrived, you now have to train it. When it's a train, or fine tune it, design it to fit your purpose. So he started working on this, get the keys, put all the cables together, now do programming. And this programming alone, programming this, writing a program for this receiver alone, it's not a matter of a year or two. So I may say it takes us about 3 years minus 1 year for COVID. So technically it takes us about almost a year to do all the calculation, the analysis, the software, the design, and all those things. And the second year we take to our development, and before COVID set in, so we're set back. So when I put it all together, it's 3 years, but technically it's around 2 years or 2.5 years, I may say. So what are the challenges? The challenges are great. Sometimes you'll be fixing things or working things and they are not, or putting them, they are not working. You try and try and try and look as if you have to give up. And sometimes you could be in lab and working from morning, and it's almost like 3 p.m. once you have really forgotten that you have not eaten. Even if you are working in the evening, you will working in the evening, and before you notice, around 4 a.m. You are trying to fix one problem. And some of the challenges, if you leave it and come back, sometimes it's good. You take a break and come back and come and continue. But some of them, when you leave and come back, it's like you have to start from the scratch. So these are some of the challenges. And yeah, there are others, but I think these are the basic one that I'll be able to give that will help you for this. So mostly before these telescopes are built, is like collaboration, funding from between government agency or bodies to be able to put this together. So that is how it is. Yeah, thank you.
Thank you very much.
Okay, thank you so much, Albert. Thank you, everyone. Our time is up. We have been really taught about how telescopes work and how they can be built. So thank you to Albert. Thank you, everyone, for coming to our monthly seminar. We hope that you continue to join us and we get to learn and advance together. Thank you, and we'll see you again next month.